draw a parallel. And then we draw the line through D. It cuts AC and AB and E and F. All right, so it's going to be any line. Seems like it. Cuts. So this should be F. And this should be E. Oh, such that EFBC is cyclic. Oh, so it's probably better to do the problem the other way. Start with the cyclic quadrilateral, and then, yeah. So let me do it that way. Yeah, this is kind of a, I don't know why they stated the problem this way, but you start with BFEC being a cyclic quadrilateral, and then you can construct the rest. It's probably a better way to do it. Okay. So we'd have BFEC. BF. I don't know if I'm labeling these right. But let's see. And then you see where those intersect, I think. Let's see. And then you draw the parallel to BF through that intersection point. I think that's kind of how it works.
To BC, right?
It should be what?
Wait. I think, wait, don't you intersect BF and CE? And then, because ABC are not collinear. Or you just need to rename the points, I think.
Correct. So if this is B, wait, what just happened? You name this C. Yeah, so I think, let's try this. So, oops. So, they draw a parallel. So, D, so it cuts AC and AB. Okay, so I let EF meet this at D. And I think that should be good. All right. I don't want it to look isosceles, but I think that looks good. So M is the midpoint of BC. And we want to see, where does that line intersect AM? Point G. Oops. And then we take the midpoint of DG. That's N. And H is the intersection of that circle with NA. And then we want to show AFE is tangent to, is that really true? Oh, it is true. Okay, interesting. So it looks like a homothetic type problem. There's probably some other point, I'm guessing, on this circle. Usually that's how it is.
So we know that AD is a tangent to the circle AFE, and using GeoGebra, it appears that the other tangent and AM, that like D is the pole of AM with respect to the circle AFE, but I don't yet know
So
how
yeah,
far.
so this point is the other tangency. So this is a harmonic quad. Interesting. So yeah, we have two midpoints. So that makes me wonder if ABC and ABG are just similar. Seems very likely. Not 100% sure, but they're not. Okay, so it looks like this is harmonic AGEF.
How do you show that AFI is harmonic?
We haven't yet. Oh, but actually, I think it's
Oh,
easy because you just project the 4 points onto BC, so that's how we know it's harmonic. Because you said you could prove that VA was tangent, right?
Yeah, it's well known that the circumcenter of AFE lies on the altitude.
Okay, so like you could prove it's tangent because angle DAC, yeah, because angle DAC is ACB is AFE. So yeah, we know it's tangent, and then just projecting these 4 points onto BC, you get BCM and infinity, so that means that AFIE is harmonic. So AI is the polar of B, we know that. All right. So we could either try to draw this point and show a homothetic. Is this perpendicular? No, not necessarily. 1 sec, I'll be right back. All right, thanks for waiting. It's 10:33.
So if you draw the circumcenter of DNH and connect it to N, it appears that that is actually perpendicular to AD,
Interesting.
which I'm pretty sure would solve the problem. Because then
Okay.
we just know that, I think, then we just know that the homothetic at H that takes A to N also takes the circles to each other.
All right. Yeah, because we know AK is perpendicular to AD. So if we knew JN was perpendicular,
Is JMN collinear?
or what did you say? Then JH and K would be collinear.
I asked, is it JMN collinear?
Oh, no, they're not. It's close, but like you can see there, it's not. So yeah, we have to use somewhere that N is the midpoint of DG. So we won't be able to solve the problem unless we use that. All right. Let's see. So yeah, I don't know if it's worth letting DH meet the circle at a point. What if we try to use that N as a midpoint by projecting? So if we take BNG infinity and we project through, basically that's equivalent to saying that if we draw the parallel through A, BG, then that means that AHIL is harmonic. And I wonder if, which means that DH and L are collinear. Okay, that's pretty valuable. So DH and L are collinear. Does that just solve the problem? Because if AL is parallel to DN, so yeah, so basically AHL and DHN are similar, and that solves the problem. So yeah, that's easy.
Wait, how did you define L?
So we draw the parallel through A to EF, or to this whole line, and we let it meet the circle at point L.
Okay.
And then basically, if you project B and G infinity onto the circle, then you get quadrilateral AHIL. So AHIL has to be harmonic. And that means that B, H, and L are collinear. Does that sound right?
Why are they similar then?
Then they're similar because basically AL is parallel to DM.
Oh, right. Yeah.
And then AH and N are collinear. So yeah, two out of the three angles are equal. So yeah, they're similar, and then the homothetic solves it. So yeah, easy problem. Okay, so step one is we want to show so first of all, AFIE is harmonic. So let AM intersect AFB at I hope they get rid of this. This was not like this before where it would keep popping up. Let AM intersect AFB at I. Then so first we're going to show AD is parallel to BC. So angle DAE is DAC. DAE is DAC, which is ABC, which is what's that? That is AFB. So that implies DA's tangent. Tangent AFB. Okay. And then we have this, and then projecting onto BC. Well, projecting through A onto the circle, actually. We have BC M, and then infinity is equal to, what's that equal to? FEA or FEIM. So this is -1. And that implies FEIM is harmonic. So then that means that, sorry, FEIA should be A and A. Did we even use that fact? I don't think we did use that, did we?
We wanted to show that D is on the polar of AE, because that allows us to prove that DHL are collinear if that is harmonic.
Oh, yeah, you're right. You're right. So that means that DI is tangent to AFB. And then we use that later. All right. Okay, so let the parallel through A to EF meet AFB at L. Or So I was just trying to use the fact that n is the midpoint. So projecting through A onto the circle, we have dgn infinity. dgn infinity is aihl. So and that means that D, H, and L are collinear. Okay. And then so LAH is similar to HMD. Since LN is parallel to is it DH? I think it's DH. Sorry, LA is parallel to DN. And oh, that's so weird. So I selected both of those, they both move at the same time. So a homothety at H takes those triangles to each other, so the circles are tangent. All right, let's check out what problems are next. So yeah, basically we just use the midpoints to create harmonic quadrilaterals. That's like the whole point of this problem. Once you do that, it's pretty easy. This is kind of interesting. Maybe this will be harder. So we have a triangle ABC and D is on BC. P is such that AP is perpendicular to BC, so P is like a point that moves. Seems like. Let's call this R, and this is P. So this looks like it might be harder, maybe. We project P onto AD. That's K. So PKD are cyclic. Then we draw the circumcircles of KAB, KAC, and we see where they cut the sides again. So let's see if I can make it. Yeah, this is going to cut AB like far away. I wonder if I can make it where it cuts each side internally. I don't think think it might be impossible though. Let's see. Oh, maybe is it possible to make this so each side is cut internally? Well, probably not. So in that case, I'll just extend both of them and see where it cuts them. Just don't want one of them to be like so far away. Maybe something like this. So E and F. EF cuts BC at Q. Prove the line passing through P and perpendicular to AQ passes through a fixed point. Okay, so this is Q. And it's saying that as P moves, this line passes through some fixed point. That point seems kind of far away, actually. Show the trace of it. Oh, that point is like right there. Interesting. All right. So we'll draw the foot of that perpendicular. Oops. Go. So yeah, these are all cyclic quadrilaterals right here. K is the projection of P onto AB. So yeah, what is that fixed point? Is it? It's not the orthocenter. Maybe it's the circumcenter of ABC. I'm not sure that it is. I don't think so now.
I think it should depend on D in some way.
Yeah, that's a good point. So let's draw that line. Oh, do these concur? No. I was gonna say. could try this. Is it that point? Yeah, it looks like it is that point. So is there like a special case when P equals A or something? Or like when P is the foot of the altitude, you project it. P is the foot of the altitude. Doesn't really help that much. As P approaches A. Oh, I don't think it is that point because that point's moving. Yeah. No, it's not that point. It's some other point. Interesting. I was wrong about that. So yeah, let's see if we can figure out what that point is. So what if I move D? I move D like really far this way. Look at the trace of it. This line. It's like this point. And what can we say about that point? So the problem's symmetric with respect to B and C, right? Maybe angle A, maybe DH bisects angle ADH. So could be. So I could try doing that. Let's see. So let's reflect AD over line BC. And basically we want to see if this point remains the same. Maybe, maybe not. I think it's moving, right? Let's see. So let's see, does point H move? It looks like point H moves, right? So I don't think that's it. Yeah, what happens as P moves? Yeah, can we figure it out in some degenerate case? So what if, let's see, we have the circumcircles of KAB and KAC. What would those be in the degenerate case when P equals A? Yeah, that's a tricky question. Maybe we could consider when P is the orthocenter. So if P is the orthocenter, then these two would be the reflection of the circumcircle of ABC, right? So maybe we could start out by considering that case. So let's say P was really the orthocenter. K would be the Humpty point. Well, we don't know. Yeah, K could still be anything. That's the problem. Let P equal R. And then, yeah, like I'm not sure, even in a special case, I'm not sure what it would be. Yeah, as P approaches A, can we say anything about the two circles KAB and KAC? They approach something. All right. So KRG is like the pedal triangle P. And AQD. Okay, I'm going to try to find that fixed point again. So let me draw the trace of this. That fixed point is right there. It's not, let's see. What's special about that? Is it cyclic with something? It's an unusual point. It has to depend on D. So it depends A, B, C, and D. But other than that, it's not so clear. So you'd have HGF and HGQ are 90 degrees. Oh yeah, that's the issue. It moves when I do that, but it's always going to pass through that point. So if I pick another point and I move it really close to it, then I move P, should always pass through I. That's interesting. I was going to say, so the problem symmetric with respect to B and C. So it wouldn't be that AB, maybe it's some angle condition on BIC or something. What if BAB equals BIB and well, and CAB was CIB, but then BAC would have to equal BIC. So that's not true. let's see. This is a hard problem. Let's see what time it is. It's 11:09. Did we do all the other ones? Let's see. Yeah. This is the last of the 6, so we could keep working on this and for another, I don't know, maybe 10 minutes. If we can't get much farther, we could try a different one. Or I could go look for something. Yeah, I think we should try to find more about, like, instead of just focusing on this point first, maybe try to learn more about the structure of the rest of the diagram. So point Q, what can we say about that? So for EF meets BC, yeah, what do we know about KAB and KAC, those circles? This makes it look like KAB passes through R, but that's not true in general. Can we prove it in a specific case for point D? Like, what if D is the midpoint of BC? Or so if K were the Humpty point, I know it's not, but if it were, could we say anything? I'm just trying to think of one special case where we could figure out the problem. All right, you wanna look for a different problem, or what do you think? Or keep working on this one?
I don't know. I think we can make progress, but I don't know.
Okay, let's do this one for like another 5 minutes. Yeah, it's such a flexible configuration. Like you have any point on BC and you have any point on altitude. But yeah, if P is the orthocenter and B is the midpoint of BC, is it, do we, yeah, I don't know. So if K were the in-center, so if AD were the angle bisector and KB was the K was in-center, then we could like use the in-center x-center lemma maybe.
There's so many circles through K. Maybe we can just try inverting around it. Because like we have like PRKD, we have AKPG, the two ones that are already drawn in.
Yeah, let's try it. So
Wait.
so you want to invert about arbitrary an arbitrary radius?
Yeah. Wait, I don't. It'd be kind of hard to, because K is a moving point in the configuration.
Yeah.
I think we can only like learn things about the problem that way, but not actually solve it.
Okay.
I'm not actually that sure how good that is.
All right. I'll hold off for now then. Yeah, we could like take this circle. Let's just see. So if we invert this circle, we'd get that. And if we invert this circle, we'd get that. And then KPRD. Invert that. Get that line. Yeah, it's crazy that I can't even figure out this problem in any special case. So what if we let D, what if D gets close to the foot of the altitude? Can we do some kind of limiting argument? So then P would equal K, so it would really be the circumcircles of PAB and PAC, right? And then, yeah, as D,
Wait.
sorry, go ahead.
Sorry, I was interrupting you.
Oh, but yeah, that's all I was gonna say.
Okay, I think I found the point.
Yeah.
Because there's a circle QGKD.
Interesting.
And that's where like the fixed point lies on that circle as well.
Oh, that's interesting.
Or at least wait. No. No, I'm no longer sure. Oh, it doesn't lie on this circle.
Oh, really?
Are
you sure?
I'm not sure. But as I move P, it looks like it just like moves ever so slightly.
So let's see.
Yeah, it does move. But that's still a circle. Why is that a circle?
That's hard to tell. Let's see. Yeah, really, I have to draw a point in the middle of nowhere and then move it to the intersection. Then move P. Could be true. So but I'm not so sure.
Yeah, I don't think it's true, but it's still an interesting circle.
Yeah. So
Oh, I think it's because the circumcenter of AGK lies on the altitude of A.
yeah.
It's the same configuration as in the last problem.
Oh, are you saying just the proof that this is cyclic?
Yeah.
Well, if we know that if we let G be the foot of the perpendicular from P, then it's just power of a point, because AG times AQ is AP times AR is AK times AD.
Oh yeah. Yeah.
That's all good. Yeah. Maybe we could invert about A with radius like square root of AP times AR and see what it does to the rest of the diagram. What was this circle? I don't remember. But yeah, I would be, because then so A would go to the point of infinity, K and B would swap. We'd see where B goes. So yeah, what if we inverted about A with radius AP times AR? So yeah, we'd have to see where B and C go. That's the only thing.
Maybe we just invert around A with like a fixed radius such that it doesn't depend on P, because then we can still move P.
Oh yeah.
And we move like just a line perpendicular to perpendicular to AR. and we can still like show the problem.
Okay. Yeah, I know, but like you said, yeah, you don't really want to invert about something that depends on P. So do a fixed, let's see. We could just pick some kind of fixed radius and invert everything about that. I'm not sure how much that would help though. Let's see. Yeah, let's think. As P approaches, or as D approaches the foot of the altitude, P approaches K. Does EF become parallel to BC? Or I think it might. So then that would kind of make it not most worthwhile. But because then, well, it shouldn't necessarily be parallel because it's where AC and AB meet those two circles. So there's no reason why that should necessarily be parallel. So basically, yeah, what if we try to prove it in the case where D equals R? So we would have an arbitrary point on the altitude. We would take the two circumcircles, and we would let AC and AB meet at E and F. And then we would draw the intersection of EF and BC, and then we take a perpendicular. So yeah, let's try it in that case. So yeah. You want to start by you want to start by seeing what the fixed point is in that case when D equals R. Actually, I might be able to just do it like this. Let's see. So then we want to draw. See if I make this look a little better. Let's see. Maybe like that. So we want to see. I know this is kind of a mess, but I'll change that soon. So this moves. Show the trace. It's like this point right here. What would be special about that point? It's such a random point because you just have a triangle ABC and B is the foot of the altitude, and somehow that point is special. Oh, you know what? I wonder. What is the circum? Center ABC. Like what would that point? How would that point at all be special? Let's see. Oops. I didn't want to draw I on. Okay. I just want to take a random point and move it to where I is. Then I'm saying, yeah, what the heck would be special about that point? Somehow it's just moved a little bit, but it's the idea. We have, yeah, KAB and KAC. Maybe making K the midpoint of AD somehow makes it easier. Maybe, like, what if we consider where K is the, let me go back. Instead of fixing B, what if we make it so that like P equals R? I tried that before. Yeah, I don't really know what that would do. All right, let's try another problem. GeoGebra. Okay, so here is the Geometry Marathon. And 17, 18. Sorry, I gotta refresh it. Yeah, I don't want to see the solution, but people should hide hide their solutions in this. Let's see. This one I think we did. So let's go to slow. Yeah, that's the one we just did. It had like 2 midpoints. And then, oh, whoops, that's Telep-Cole solution. He or she, I don't know who Telep-Cole is, but they usually give very hard problems. So, oh, he gave like 4 versions of the same problem. Okay, so what about, wow, that looks hard. Let's see, what's problem 21? So we have a circle tangent. I don't like circle tangency problems. Let's see if this guy has a better problem. I also don't like weird conditions like that. Let's see problem 23. It's got a Gergonne point. Let's see. These are hard problems. What about? Well, I think I've seen this before. Let's try this. So we reflect I with respect to DE, EF, and DF. This is a kind of weird notation. Let's try this one and see. Prove that H, I2 prime, G, I prime, and J. What are GH? Yeah, they didn't. Oh, they're the midpoints. Okay, so yeah, let's try this one. This one looks kind of interesting. Don't know why they chose those names for the points, but let's see. What if I call these like X, Y, and Z instead? So I feel like that would make me feel a little better. So I1 prime is X. And then this I prime will say is Y. And I2 prime will say is Z. Okay. Let's maximize this. Okay, so we have a triangle ABC, and we draw the incircle. I might even have a tool that does. Oh, I forgot to download the tool, but whatever. I'll just do it the old-fashioned way. So this is DEF, and then the midpoints are GH and J. G. It says A, B, B, C, and C, A. So it would be G, H, and J. Right? And we reflect I over, let's see. Yeah, it's hard to get point F here. All right. So let's reflect I over those three segments. To get X, Y, and Z. And then I over EF is Y. And then this is Z. And we want to show that H, Z, G, Y, and J, X are concurrent. Maybe they meant, I wonder if they meant to say B, C, C, A, and A, B. So like this, and this are concurrent. Yeah, I think they meant to say like B, C, C, A, and A, B. Because if you do the problem like that, H, Z, G, Y, and J, X doesn't look like it. Yeah, so yeah, so I'll relabel them to fit the problem. G, H, and J. And we want to show that those concur. Kind of interesting. All right. So it looks like I kind of lies on JX, but it's hard to get everything perfect in the diagram. Maybe that looks okay. So you have like all these kites. So that's a kite, that's a kite, that's a kite. So basically, you draw X, Y, Z. But let me draw the midpoints of EF, DE, and EF. So XYZ is homothetic to KLM. And an inversion of KLM about the end circle takes it to ABC. So an inversion of XYZ about the end circle would take it to ABC with half the like half the size. Would be the midpoints of IA, IB, and IC. That's interesting. So basically, if you invert X, Y, and Z, they would go to the midpoints of IA, IB, and IC. So maybe we can we use the SARGs? And the thing is, like inversion, I don't know how much inversion helps with showing concurrency. like this. Maybe it does. Oh, is BZXC cyclic? It looks like these are. That might make it a lot easier. Maybe that's just true by power of a point. It's probably true by power of a point because, yeah, it is true by power of a point. So BZXC is cyclic, and similarly for the others. All right. Also, BKMC is cyclic, but we're not using that for now. So I has the same power with respect to those three. And then these are the midpoints of the chords of each of the circles. We want to show that X, Y, Z, and G, H, J are perspective. Maybe the SARGs does help. I was afraid to use the SARGs because it looks a little messy. But maybe it's the way to go. So it's like we want to take the medial triangle of ABC and see where it meets yeah, but those points are kind of hard to pin down. But if they were concurrent, let's say they were concurrent, what would happen if we did a homothetic with ratio 2? So I wonder. You know, what is the Chevian's nest theorem? I always forget what it is, but I think that might be able to apply to this.
Well, if you have like 3 concurrent Chevians and they form a triangle, and that in that triangle you again have 3 concurrent Chevians, and you always mark like well, it's kind of difficult to describe. You mark like the feet of those Chevians onto the opposite sides, and then you connect these with the vertices of the original triangle.
So yeah, I see. Now I remember once you said that. Yeah. So I wonder if dy, ez, and fx concur, because then if that were true, we could use the Chebyshev nest theorem, right? So dy, fx, and ez, it looks like they do. So if we can show that those concur, then the problem follows from the Chebyshev nest theorem. Okay.
Wait, why?
Because AD, BE, and CF concur. And so, oh, actually, maybe not. Yeah, because to use the Chebyshev nest theorem, we need to have 3 segments from A, B, and C if we wanted to do that. HC, GY, JX. So yeah, we could try to use trig-Cheba on triangle GHJ. We need some angles though. So JG we know is parallel to AC, but we need the angle that GY makes with AC. Actually, maybe this is bashable by so here's what I'm thinking. So we start with triangle GHJ, and we try to use trig-Cheba. So we try to show sine JGY over sine HGY, blah blah blah, is equal to 1. But to find JGY, that's the angle that JG makes with GY, and JG is parallel to AC, so that's the angle that AC makes with GY. And I wonder if we can calculate that somehow, because AY C is cyclic. So angle GYX is angle ACX, and So yeah, we need to show if you take the angle that GY makes with AC and the angle that GY makes with AB and take the ratio of the sines of those and multiply it cyclically, we want to show that's 1. Yeah, it's still tricky. I wonder if GL, HK, and JM are linear. GL, JM, and HK. It's hard to see. I think so. So GL, HK, and JM. It looks like those are collinear. That might be, maybe that's the Chevian's nest theorem. Let me think about that. So, no, that wouldn't be the Chevian's nest theorem. GL, JM, and HK. Because that triangle is basically half of XYZ. So I wonder if we could show that those are collinear. Then maybe we could show that if we double the triangle, it's still collinear. So like, instead of trying to show for XYZ, I'm trying to show for KLM. But even that doesn't seem that easy. Hard problem. All right, 2 more minutes. Then we will stop. All right, I think I'm gonna stop here. So yeah, thanks for sticking around, Johannes and Georgie. Yeah, it was fun, and yeah, we got through a lot of problems, so they were a little bit easier this time. So for all of you watching, if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So thanks again for watching and have a great day.